Katangi tatiti, katangi takaka, katangi hoki ko aho, te he moriora. Engamana, engarea, ingata wida pumanua, ro rakatida ma, tenakoto, tenatato katoa. Norera, ko waio, ko Harleen Hain, tako ingawa, ko te tumiaki o te wharewanaka o Otago aho. Namihi, nako kiakoto, tenakoto, tenatato katoa. Welcome, everyone. My name is Harleen Hain, and I have the great privilege of being the Vice Chancellor here at the University of Otago. And I am delighted to welcome each and every one of you to this inaugural professorial lecture for Professor John Reynolds. As usual, when I look out on the audience, I see both staff and students from the University of Otago. And I also see members of the Dunedin public who very rightly use these inaugural professorial lectures as a way of continuing their own lifelong learning opportunities. I'd also like to extend a particularly warm welcome to the members of John's family who have been here or who have come here this evening to share in this celebration. I'd like to acknowledge his wife, Jane, his sons, Daniel and Fraser, his daughter, Eva, his mother and father-in-law, Rosemary and Maurice, his sister and brother-in-law, Irene and Kevin, who have flown in from Wellington. A number of other family members and friends have also journeyed to be here, Lloyd and Charmian, Peter and Anne from Christchurch, and Adrian and Chris from Gore. On behalf of the University of Otago, I would be very pleased to welcome all of you to this event, and I'm sure that your presence here this evening will make the evening even more special for John. Now, those of you who attend these IPLs regularly will know that achieving the rank of professor is not an easy task. The university sets extremely high expectations for candidates for this position, and those who are successfully promoted must have demonstrated excellence in teaching, in research, and in service to the university and the wider community. Professor Reynolds certainly has demonstrated excellence in all three of these categories. John is undeniably an outstanding and highly respected teacher. Much of his motivation to be a good teacher has come from his own experiences a little while ago as a medical student. His desire to become the kind of teacher that inspired him while he was studying has been richly rewarded with the National Teaching Award. John also has an international reputation for research. He's a recognized authority on synaptic transmission and neural plasticity, and his papers are often published in highly ranking journals, including Nature, the Journal of Neuroscience, and the Journal of Physiology. Now, in addition to all of this, John also has a service record that is second to none. Over the years, he has served on a number of high-level service roles here at Otago, and most recently, he has accepted the challenge of being the Director of Health Sciences first year, where he has spent the most of this year helping us work our way through some extremely important changes to our curriculum. Now, this has not been an easy task, but it's been an extremely important and fruitful one. I personally have really enjoyed working with John, and I have come to value not only his very high IQ, but also his very high EQ as well. So, John, on behalf of the University of Otago, I would like to warmly congratulate you on your well-earned promotion to the rank of professor. And before we invite Professor Reynolds to give his inaugural professorial lecture, I will first call on Professor Vernon Ward, who is the Dean of the School of Biomedical Sciences, who will tell us just a little bit more about John's academic whakapapa. Nō reira, tēnā koutou, tenatato katoa.
Thank you, Vice-Chancellor. Tēnā koutou katoa, me nui tēnā kia koutou. Welcome, everybody. It's great to see everybody here. What a great turnout of anatomists and neuroscientists and all sorts sitting out there staring at me. I have the pleasure of introducing Professor Reynolds to you this evening, and it is very much a privilege that I get to do this, and it is a pleasure. because I get to look at people's backgrounds and I get to see some of what they've done and I get to present that to you. I hope always that it makes them slightly nervous that I'm doing this. It may interest you to know that for the first 10 years of his working life, John was an electronics technician. He made it very clear that's not an electrician, it's an electronics technician. And you'll see some of that this evening. He gained an NZCE in electronics along the way. And then there was in his record of where he worked, there's this gap of about 5 or 6 years, which the Vice-Chancellor has alluded to already, because he suddenly appeared with an MBCHB from Otago in 1994 and was a resident medical officer in Whangarei. He then headed off down a research path before getting a PhD. There's not that many that have gone through that particular path, and I think he's to be congratulated on that. It's not an easy one. So he's ended up with both a medical degree and a PhD in separate stints. He became a senior lecturer here in 2005, an associate professor in 2011, and a professor in 2017. So what are some of the hallmarks of John's career that have allowed that progression to happen? Well, if you look at the last 10 years, he's brought in over $12 million worth of external research income, and he's been a principal investigator on funding from MBIE, the Brain Research New Zealand Centre of Research Excellence, the Neurological Foundation, the Health Research Council, the Marsden Fund. He's been a Rutherford Discovery Fellow, and he's on many other grants that he hasn't been the PI on. He's won multiple early career research awards. He's published 56 refereed journal articles, and as already mentioned, Nature Communications, Journal Neuroscience, Trends in Neuroscience, and all the places that we'd like to see ourselves published in. As already mentioned, he's an excellent teacher, and I'm sort of scanning them out here because there's a chance that the person who awarded him or presented him with his National Teaching Award, Ako Aotearoa, is here. I can't quite see him, but that was in 2008. And in case you're not aware, we are aware because Vice-Chancellor just mentioned it to you, but that Director of Health Science first year is a major leadership role that he's taking on in university. It's not easy, it's a challenging role. And in case you weren't aware, it's a 0.6 FTE. So that's more than half time doing that job. He's an excellent commitment to science leadership. He's been a member of the Otago Ozone Group, a member of the Directorate of the New Zealand Brain Research Centre of Research Excellence. He's on the Science Management Group that put together the successful National Science Challenge for the Ageing Well proposal, and he's the incoming president of the International Basal Ganglia Society. So there's a lot of service stuff there, a lot of leadership there. And he wouldn't have a teaching award unless he could communicate. And some of the things that he's done in the last few years, he's recently been interviewed by Nigel Letta for some episodes on The Curious Mind, the ODT, New Zealand Herald, Radio New Zealand, Scientific American, Channel 9, ABC Radio Science, and I'm sure the absolute highlight of his communication career was being interviewed by Paul Henry on TV3. So as a very broad set of contributions across that academic spectrum that we expect of our professors, and John has shown that immensely. So you've heard enough from me. You get to hear the pleasure of Professor Reynolds and his inaugural professorial lecture. You can see the title behind you, Teaching an Old Brain New Tricks. What you're going to see from John today is that pathway through medicine to neuroscience to translational neuroscience. What he's going to present you is that pathway of that basic fundamental understanding of brain reinforcement, and he's going to follow that through to how you develop treatments for Parkinson's disease, and how an accidental discovery is made along the way is starting to be used to apply to people with stroke. So I now invite Professor Reynolds to present his inaugural professorial lecture.
Thank you. Just let me take this all in for a second. Tēnā koutou katoa. Ko te mata, te maunga, ko ngā rororo te awa, ko John Reynolds aho. Tēnā koutou, tēnā tātou katoa. Vice-Chancellor Professor Harleen Hayne, thank you for your kind welcome. Dean Professor Vernon Wood, thank you very much for your kind introduction. Deputy Vice-Chancellors Professor Helen Nicholson and Professor Vernon Squire, Pro Vice-Chancellor Professor Peter Crampton, my Head of Department Professor Neil Gemmell, colleagues, my family, and my friends, those of you I know and those of you I haven't quite met, and hopefully will over a cup of tea later. So I stand here absolutely honoured to receive this recognition from my work at University of Otago over the last 20 years, which sounds like a long time. Before I really get into the theme of the talk, which is teaching an old brain new tricks, as you'll see up there, I want to start off with some thanks in case I run out of time at the end and don't get down to do it. Firstly, I want to acknowledge really my wonderful sister Irene and brother-in-law Kevin, who are here, have travelled from Wellington and always come when there's something from me. It's very special. Peter and Anne, who've come from Christchurch. I also want to acknowledge my extended family on the Smith side who are here, especially my mother-in-law and friend, Rosemary, and her husband, Morris. I think I've missed a few people out, haven't I? I wonder where they are. So most importantly, I'm really incredibly indebted to these wonderful people who refuse to let all the work and the crazy working hours get in the way of the laughter. Heartfelt thanks to my wonderful wife, Jane, and my amazing children, some of whom are no longer children. Can't see the other one. Where is he? He's not here. Oh, there he is. Good. Daniel, Fraser, and Eva. Finally, thank you to you all for coming here tonight and for helping me celebrate this honour. Kia ora. So I've been asked to first talk a little bit about my life journey and how it all brought me to this point. So here goes. So I was born in Hastings in Hawke's Bay in 1963. So if you can quickly do the maths, you'll be able to work it out. Here I am with my brother Clive and my mother Connie. And I was a little runt at this stage, and I think I took off to Karatani for a few weeks after this. Fast forward a few years later, and this is my brother and I with my mum and dad. And when you see my brother and I, for some reason, he's always standing on my left-hand side. So if you see two woolly people in the next view, he's always on your right and I'm on the left. But anyway. So my father, Bob, worked for the power board in Hastings as a control operator and a fitter and turner. And I really believe that it was his input that definitely spawned my interest in working with my hands, especially on electronics projects. Now, my mother unfortunately became disabled not so long after this photo was taken. I think that was probably a source of quite some unhappiness in our family subsequent to that time. In hindsight, it may well also have been one of my drivers to really gravitate towards the healthcare profession. But enough of the sad things, let's think of the things that were good back then. And I really think, anyone from Hawke's Bay here? Yeah, yes, there you go. I didn't know that about you. I'm going to have to have a coffee and talk about that. But really, it's the summers that set Hawke's Bay apart from everywhere else. I'm sorry to say, it's lovely here, but. So I spent a lot of summers. So here's me with my woolly hair, and there's my brother, and there's my cousins that you can see are all a bit like that too. That's actually Irene's son there. And we spent a lot of time fishing by the river there and just hanging out and swimming in that river, the Inaugural, which is really my river, I think. But I've also indicated here an arrow, and that really isn't the spot there where we had the best fishing. That was actually the spot that I lost one of my 9 lives. So a very short story here. So I was out there one day with my friend Reese in his dad's car, and he decided to gun it along that bank, as 17-year-olds tend to do. And of course, unfortunately, what happened is he caused some damage to the rear suspension of his dad's classic Zephyr. Oops. Now, luckily, there were other friends there with cars there that day, and although I offered to go home with him and really share the blame, he said, no, you stay, come home with them. And I think that was probably a good thing to have done, because there must have been damage to the steering. His car failed to negotiate a bend on the way home and rolled down a bank. He was okay, but where I was sitting, the roof was flat. So I may not have been here talking to you if that had happened. So one of my 9 lives down, anyway. Other than that, I sort of remember the summers in the bay very fondly. So here I am with my woolly hair. So you could always wear your shorts and bare feet there and shirt off and let your hair grow wild. And summer days back then were often finished with great degrees of pain because I think we'd never heard of sunblock. I think we used number 3, which we thought was, that's pretty wimpy. And I think it was like water, really. But anyway. So a year or two after that picture up there was taken, my mother unfortunately passed away and left the 3 of us to carry on through life. So, as to how I got here and career-wise, everyone has to have a quotation. I'm not very big on quotations, but I found this one from American poet and novelist Don Williams Jr., who wrote, "The road of life twists and turns and no 2 directions are ever the same, yet our lessons come from the journey, not the destination." I think that's absolutely what's happened with me. So at the end of school, I wanted to go to Canterbury to study electronics. That was what I wrote down on my little form in the 7th form. And however, I was advised that I wouldn't be able to enter the engineering intermediate because I hadn't done chemistry. I was told this by the person who 2 years before had told me to drop chemistry and do languages. I could still see the beads of sweat in his face. But anyway, Now, I came from a family really that we had no idea about going to school from going to university from school. So we didn't really know that it actually was very possible, the wonderful chemistry department we have, and in Christchurch and all around the country, that you could actually get up to a stage to get there. So in fact, I decided not to go down that pathway, although I did actually manage to pick up chemistry 9 years later when I went to medical school. But anyway, so I decided, excuse the moustache, that I would leave school and study. It was big in the 80s, we all had moustaches. And leave school and study electronics in the industry, because I thought there would be a way that I could eventually go into engineering later. Turned out really the right decision for me. Here I am on my 21st actually at work in Palmerston North Hospital. I then went from there to become a technical manager for a medical company in Wellington, where I was designing and servicing medical equipment. So I think that way got me exposed to patients and medical consultants in my work. I had some fantastic friends, very close friends in the medical and nursing care professions, and started to get convinced that maybe I could possibly go down and do medicine. So I gave up the working life in the company car and came down here to Dunedin to do my medical intermediate. So here's the medical class. You won't really be able to see me and all that, so I've put an arrow there. You can see me over there. And if you look very carefully, you might spot something else that's rather interesting over this side. So you see it? Three very important people over the left-hand side there. And then fast forward 5 years later and we get to our graduating class, and there's me in the middle. I'm not allowed to use the laser pointer, but I'll do. There it is there. Oops, can't do it. And if you look way over the other side, one of those nurses graduated to get a straitjacket. So there we go. One of those nuns, graduated to get a straitjacket. So I don't know if that's a natural transition, but that's what happened. So off I went to practice medicine in Whangarei. And believe it or not, in all of the times I was there, that's the only photograph I had of me being a doctor. And it actually was me in a quieter moment, of which there were very few, helping out my nursing colleagues. Now, I noticed quite poignantly at the back that someone had written something very nice there. One of the nursing staff had done. So that was quite wonderful. I didn't know that. So nicest doctor in the world will make a nurse out of you yet, which is kind of nice. Now, I remember quite soberingly much of that time in Whangarei in the mid-90s as an extremely busy, extremely stressful time. Doctoring was back then, when we as junior doctors were often left in very unsafe circumstances that we should never have been put in. I'm afraid that was my exposure to medicine, really, because I went to a small hospital. So it was nice to read that at least one group of people, the nurses, did appreciate what I did when I was there. Anyway, so I spent 2.5 years in practice there, and I chose to be in the rehabilitation unit because I really enjoyed working with people on a journey to come back from a neurological disorder or just general things that can happen to us when we get older, and to get back on their feet. And I really valued that. I found it a very positive and fascinating area of medicine, but I was also fascinated by actually, frustratingly, how little that modern medicine can actually do for these people. So the gains were made from the multidisciplinary work of the physiotherapist, the occupational therapist, the speech-language therapist, social workers, nursing staff, working with the people and their families. To be really, I suppose, to be a little controversial, the doctors are really there to juggle the medications and manage any side effects or complications. So with a lack of ongoing treatment options, once the person really has left the hospital and the available community rehab care, one could say that their bed was made and they were forced to lie in it in terms of coping with the extent of their disability. So really, to be able to improve the recovery of the brain in these situations, the realisation for me at those times really was that there's a paucity of effective drugs that we have that are able to cross this amazing barrier that stops bad things getting from the blood into the brain, called the blood-brain barrier. It's wonderful for protecting us, but it's bad for getting things through for treating our brain. And also we understand very little, and we still really understand relatively little, about how the brain circuits reorganise after injury. So those are the challenges that drove and stimulated my science journey. So, after finishing up at Whangarei, I can see one of the gentlemen in the photos up the back there. I came down to Dunedin. I got convinced by a certain gentleman, Professor Brian Hyland, that I could come and do a couple of years of research, do a thing called a PhD, which I knew nothing about, being a medic. I thought, okay, it sounds all right, but it's a long time. And I was very lucky to be supervised by these two gentlemen, Professor Brian Hyland from physiology and Professor Jeff Wickens, who's now in Okinawa. I actually discovered an interest in neuroscience from a summer studentship that I did with Brian in my medical degree, and I highly recommend to students, if you want to think about it, go do a summer studentship and see if you like it. I'm also extremely indebted to the Neurological Foundation of New Zealand, who took a chance on a doctor who didn't know much about science and gave me a chance to do a PhD. So thankfully, skip forward over many, many hours sitting in front of a rig, and I got a PhD. And along the way, I added these two lovely children, Daniel and Fraser, and who are the lanky boys in the audience that you might see later on. Now, this here is Sue, my first wife, who many of you will remember, who very sadly passed away well before her time. So I'm indebted to her for her support over those early years. So what was the PhD about? And how has it led me to what I'm researching now? Daniel, I'm sorry, I'm going to embarrass you. This is my son, Daniel, right now. And this is truly a photograph taken about 2 months before I actually started, showed up in Brian's lab and started doing some work. I didn't have any idea about this, but this is really exemplifies the whole sort of idea of the dopamine system in learning. So he's about 4 months old and he's experiencing his first Christmas. He was lucky enough to get given by Sue and I this helium-filled Father Christmas balloon. Everyone wants one of those, don't they? And he was fascinated by it. Look at his fascination. So, of course, Sue and I placed him in his jolly jumper and tied the balloon to the jumper, right? And any of you who have had young babies in your lives will know that babies do emit these sort of random kind of movements if you sit there. And we would sort of turn our back a little bit, and we'd turn back, and suddenly he's holding this balloon like this. And then he'd let it go. Oh, that's funny. And then he'd do it again. And what we would notice is that the time in between those episodes of him grabbing it got shorter and shorter and shorter. What Daniel's brain was doing, his basal ganglia was doing, was stamping out those wasteful movements that do nothing and stamping in the one thing that he wanted to do, which was to grab that balloon. That really was reward-related learning online for us to see. So goal-directed learning, if you like, January 1997. Thank you to Daniel Reynolds. Right. Yes, I think it's worth that. So he was demonstrating to us two processes. Motivation. You've got a goal, you're motivated to get it, you will direct your actions towards that until you get it. It's called goal-directed learning, and it's well known that both motivation and goal-directed learning, both are processes that use this neurochemical called dopamine. So dopamine, it's more than a pleasure chemical. It's manufactured in areas here at the base of the brain, and it's passed into areas in the front that are involved in motivation, and this area here, the basal ganglia, for learning. But what we tend to think about in the public is that dopamine's the happy chemical, right? It actually is a happy chemical. If I gave you a shot of dopamine now, you'd probably be very happy with me, and maybe occasionally you are getting a shot of dopamine if something comes to you, but it actually is a lot more than that, because dopamine, the happiness can go away even though you're getting dopamine around, and it happens in drug addiction. So really, here's a little bit of the science behind this thing. First of all, there's a system there in the front of the brain from the area called the VTA, where the dopamine cells live, that really helps you learn the value of a stimulus. Because you don't know, a stimulus is a thing in the environment. I don't know if that sign's good when I first see it. Does it mean something important? It might mean get the heck out of here in a hurry. So you need to actually understand what stimuli really mean in terms of the actions that they drive. And for Daniel, it was bright, floaty things are cool. Go get it, tiger, right? That was what that motivational thing was doing. It was throwing dopamine to his frontal areas, and he just had to work out what the heck to do to go and grab that. There's another, there's many areas of dopamine, that dopamine cells live, but this particular one everyone mostly knows about is the substantia nigra, which projects forward into the striatum here. And that's really learning, what do I need to do to get that stimulus? So the first thing is, it's a stimulus, it's a balloon, it's cool, I've got to go and get it. The second thing is, what thing do I have to do to get it successfully? And that's what the dopamine cell system is trying to solve all the time. So grab, in his case, it was grab the string the right way. Work out how to grab it so that I can have that thing sitting up close to me. I'll stop talking about you now, Daniel, that's all right. Now, together, obviously, the systems in the brain are much more complex, so I'd like you to learn this if you don't mind, and we'll ask you some questions about it later. That's just to show you how incredibly complex this system is. Okay, and lots of neurochemicals in there. I'm not going to do that. I'm going to give you, I found actually on a popular blog, actually, a very simple system to understand it. So well done, this person, for understanding it. And really, if you think about it as this sort of flow chart here, we have an intent to do a behaviour, all right? That's the thing that drives us to do. Goal-directed. It could be come to work to earn some money, okay? We do earn money still, don't we? Yes, we do. And then you emit a behaviour. You emit a behaviour towards that goal. If you get it right, you get a big dopamine pulse. And what that dopamine pulse does is it makes you feel good. Oh, I'm proud of myself, I've got the balloon, and you want to repeat it. Actually, the circuit goes round and round and round because after a while you get better and better at it. You successfully do the behaviour, you get some dopamine released, you want to do it again, and it goes around. But actually, after a while, you lose the pleasure side of things and it becomes a habit, which is fine. Can you imagine if all of the time you had to think about what you had to do to earn something? You had to constantly think, okay, I've got to get out of the chair, right, so I think I'd do it this way, right? Okay, that's right, that's fine. People with Parkinson's, their habit systems are impaired and they are constantly in this goal-directed mode. So you can imagine with people with Parkinson's how tiring this can be because you're constantly in this goal-directed mode. And another analogy really, or another thought application is in drug addiction, where this suddenly, you still get your dopamine released in the brain because the drugs will drive the dopamine release. It's the way it works. But actually you lose the feeling good and it just becomes the absolute need to take drugs. And it becomes just something that becomes your total motivation is to do everything you can to take drugs, and it's not as for a pleasurable experience. So that process there of getting some dopamine and doing the thing again, we call reinforcement. And you know about positive reinforcement. Sit to the dog sits, and then you give them the food. The timing is obviously inherently important. If you give them the food and then say sit, what do? Negative reinforcement is really actually learning to do something to stop a stimulus from happening. So it could be learning that if you don't go and do your study, Fraser Reynolds, that your father will emit a behaviour where he tells you that you need to get in there and do it. So you do your study, right? And then it becomes a negative reinforcer because you've learned what you need to do to stop the terrible thing of the father yelling at you. So my PhD really was a very simple thing, what happens in the brain during reinforcement. So it really influences the formation of movement memories in this area that we talked about called the striatum. This is an MRI taken this way, and if you were to put a slice down here and go coronally for you anatomists that are here and look on to a slice here, which actually came from the Anatomy Museum, you can see the structures that we're talking about. This cerebral cortex is this wonderful area around the outside where we learn to love, to think, to reason, have memory, enjoy music. Everything that we can do as higher mammals is really in our cortex. But we have this area here, which is also in the crocodile, which is an area really that's focused on trying to learn what you need to do to achieve things, and that's the striatum. And the dopamine cells live down in the midbrain and they release their dopamine into this area. So my task was to have a look in here and have a look and see what happens at the cellular level. So if we take a little spot here and we blow it up, then you'll see one of these neurons that became my friends over many, many nights, and some of my students since have too, because you have to sit there and try and record from these things inside these cells for many hours and record what happens in their activity. This is called a spiny neuron because it has all these little tiny things called spines embedded over it, about 10,000 to 100,000 of these. If you blow one of those up, you can see one of these spines. And this spine is an area where that big cortex projects onto these cells, right? That's where the synapses live. So if you were to do it diagrammatically, that's a synapse between the neuron in the cortex and the spiny neuron right there. And what I would do is I would test synaptic function. I would test how strong these synapses are by putting an electrode in here and then trying to measure the strength of that synapse. And what we know very well is that memories are stored through changes in the strength of those synapses. And that's known throughout the brain that this occurs. The rules are different in different brain areas. The striatum has got dopamine, which adds another layer. But so to measure this, we put an electrode in here. We'd be recording inside the cell, electrode here, turn on this with a bit of electrical current, and you see this response that occurs here. Right? I'll do that again. You see a sort of a response that you can record on a machine. And we would do that over and over again. I would do that over and over again. And then what I would do is apply a certain pattern of stimulation behaviour. So maybe a burst of stimulation, and then go back and repeat it again. And what that will do is it will modulate the strength of those synapses, up or down, or may do nothing, depending on where we are. Now that's a classical paradigm where one measures what we call synaptic plasticity, the ability for synapses in the brain to change their strength after a certain pattern of activity. It turns out that it's not like the hippocampus. Those are the hippocampus people. It's quite different because dopamine makes things even an added layer of difficulty. So it changes the memory forming process. So in fact, dopamine can make, with the same pattern of activity, it can make the synapses stronger or it can make them weaker, depending on which way you hold your head. So my job was to try and work out to a degree in a whole living brain what the rules were for plasticity. So how does dopamine decide the direction of change when it's simply there and it's going to change the activity of the input and the output? So I'm going to summarise about 15 years of work, Brian, maybe. 3 easy steps to understand how dopamine works for reinforcement. I've called it the how, what and when principle, right? First of all, how do dopamine cells signal an important event? This is work in Brian's lab where Brian's people could record from individual dopamine cells in animals that can move around. And you can watch them moving around and you see when they get engaged in various activities, things that might be good for them, for example. And cut a long story very short, they fire along like a bad clock, these cells, but every so often there are these bursts, these fast, rapid-firing bursts that we know when you record the release of dopamine cause this great big super-added pulse of dopamine. And those bursts really, when you look at what's happening to the animal at the time, those bursts dopamine cells fire bursts in response to important events. It might have caused a few of you to jump, you'd have a nice big burst of dopamine right then. If I did it over and over again every 5 seconds, apart from being really annoying, your dopamine cells after a while would just habituate to that and say, well, that's not really important. I have to wait till something really important happens after that. So stimuli that are important in the environment will cause dopamine cells to fire bursts. So then with Jeff, we wanted to know what do those bursts do to the synapses? And the way we did this was actually apply the bursts back to the animal and watch their behaviour effectively. And animals will happily self-administer these bursts for as long as you want to let them do it because it's very rewarding. So we knew the characteristics of that. But what I was trying to do was to record the strength of the synapses in the brain while those bursts were arriving. Again, to cut a long story short, dopamine bursts strengthen movement-related synapses in the striatum. And we found sort of that, dopamine bursts would come along and you'd make the synapses stronger, which would tend to make you want to do the behaviour to arrive to get the burst to occur again, is really what we found out. But we had no idea of the timing then. And actually fast forward only to even this year we've published this, so I'm still been interested in it. And I had a wonderful PhD student, now Dr. Simon Fisher, who did all these recordings. And I take my hat off to the people in my lab that sit there for many hours doing these recordings because you have to have a lot of stamina. And he really worked out with my collaborators here, including Cliff Abraham from Otago, we really worked out the timing of how this all has to be. Here's the circuit again. So Simon worked out the timing of how the neuron from the cortex, when it has to fire, when the cell in the striatum has to fire, and that when those two go together, there is this thing which is called an activity trace or an eligibility trace, if you like, that really says, oh, I've had something important happen, it's made me fire, now I've got some time, and I'm waiting for this thing to result in a reward. And if the reward doesn't come in that time, then it's not that important to me and don't reinforce it. So what we found was, if this case there's no outcome, those strengthened synapses will be weakened. But when he applied a dopamine pulse, within 2 seconds of that input coming, then that said to us, strengthen the synapses. So it really is like a timing circuit saying, right, something good's happened. If it results in something, in a dopamine pulse, then I must have caused that to happen. So I moved that, I grabbed this, I got this. That means that I have caused it and you need to reinforce that. And that was published this year, telling us that dopamine selects which synapses to strengthen by targeting those that are active within a critical timing period. So that's all good. I can't get away from this desire, this love of thinking about doing things that could help people with neurological disorders. And really, we've tried to look beyond this to the implications for the ageing brain in Parkinson's disease. Now, Parkinson's disease is a disorder an age-related disorder where these dopamine cells, for really a reason we're not too sure about, they die off. And they die off quicker than neurons might be lost in those of us sitting here without Parkinson's disease. If you take a slice through the brain stem and look here, this is not stained. These are sort of unstained. This is what the normal midbrain looks like. And because of this neuromelanin, you see the dopamine cells here without staining, whereas in Parkinson's, they've gone away. And so they've died away. And when someone has more than 70% loss of those neurons, they start showing the signs and symptoms of Parkinson's. Now, what happens is we replace that dopamine that's lost by a drug called L-dopa, levodopa, because you can't give someone dopamine, it doesn't get in the brain, blood-brain barrier again, right? In fact, it makes them very sick, if anything. So the drug L-dopa was a wonder drug that came out of the 50s and 60s. If you've seen Awakenings, you'll know that Oliver Sacks was using this to awaken people. L-dopa gets in the brain, gets turned into dopamine in these surviving nerve terminals. Now, I've told you they're dying off. So when you first get Parkinson's, you've got 20-30% left. You've got room and reserve for dopamine to be created. But what happens as the deterioration goes on, these dopamine cells are dying off. L-dopa has a real trouble trying to give you a nice stable dopamine signal. And in fact, what happens is you get these like long, slow fluctuations in dopamine levels from L-dopa in the brain. This happens over hours and hours, you know. Take the pill 4 or 5 times a day. And I was told in medical school that what happens is you get side effects from this drug after 4 or 5 years. Hello, from medical school, as a colleague of mine just recognised. 4 or 5 years. That was a dopamine pulse, just recognition. No, I've just lost myself, Margaret. I was told at medical school, this is why you get these terrible side effects that occur. And here is Michael J. Fox exhibiting this one called dyskinesias. Now, he's since had surgery, so he hasn't got such a major problem, but you can see that he has this abnormal movements that he cannot control. It's a bit like the baby getting the movements back, the random movements. They come back. And we think it's because dopamine's actually been too high for too long over the day, and it's reinforcing movements that aren't useful for you. That's what we think is really going on. Because the reason we think that is actually when you look at how dopamine cells fire normally, as Brian's work shows, that really those bursts that occur are only a matter of seconds. All right? So they're only going for a matter of seconds, and yet we have this great big fluctuation that goes on for hours. So our aim as a team, I'll show you the team in a second, was to really see if we could emulate this natural changes in dopamine and on the very short seconds timescale. And you can't do that with a pill, obviously. But here's part of the team. The team's changed many times because people come and go. But this is a really important project that MB are funding. And the thing that's important about it is it includes some very clever people who are chemists, and I particularly want to acknowledge my colleague, Ying Tan, partner in crime, I could say. A number of others that are here too. So we have chemists, biologists, we have people from Otago Innovation Limited, we have our research and enterprise officer, and we have people in industry, and we're all working together to try and see if we can emulate this problem, really, to try and replace dopamine in a normal way. How might we do it? Well, we're trying to mimic the timing of the burst seen in natural reinforcement, and what we're doing is, you can imagine, this is a biological package called a liposome, a little tiny thing about 200 nanometers across, and our clever chemists can package in there certain chemicals, and what they've done is made them sensitive to a remote trigger, that we can apply a trigger diagrammatically along the timing that you see in these natural bursts, and that we will use that to deform the liposome and release the neurochemical so the brain sees the chemical coming under certain timing that looks natural. That is the aim. And the control signal that we use, here are the liposomes. The control signals we use is ultrasound. And what these guys have done is put a gold nanoparticle attached to the liposome. We affectionately call it the blingosome because it's been hanging off there. Always like that name. Granting bodies seem to like it once too, but anyway. Gold nanoparticle, and here's a picture of one that Sean over there took under the EM. You can see those little hollow gold nanoparticles. The ultrasound deforms, if you like, changes this gold nanoparticle in a different relationship to the liposome and releases the neurochemicals. And we've done proof of concept that shows that we can actually measure over a second-to-second time scale, and this is some stuff that Justine and Brian have done in their lab, have actually measured the changes in a dopamine-like agonist in the drug over seconds. So we can do it. Now we're working forward to really translate it into a model that could go into humans. Right. And that's maybe what it might look like. It might look slightly better than that one day, but I think ideally it would be a little transducer that sits underneath the scalp, doesn't go inside the skull because that becomes more invasive, and somebody would have an intravenous dose of these liposomes that will float around for a few days, and this thing will turn on when we need it to happen. That's where we're going. So our aim really is to restore normal brain plasticity in the aged Parkinson's brain, to reverse these learnt side effects that have occurred and restore normal movement learning. That's what we'd really like to do. If we could get people who've got these dyskinesias and reverse it for them, because there's nothing can be done now. If we can actually reverse it by normalising their dopamine cells, firing, or dopamine release firing, and give them good physiotherapy to stamp out those movements, just like Daniel learnt to grab the balloon, then we could really make a difference in people's lives. So what about the whole ageing of the brain? This is something we ask every day. Are we ever too old to learn? Are we too old to learn? We used to think that we just lost loads and loads of cells as we got older and older. We do lose cells as we get older, but there are things that you can do to slow this process down, and it's becoming very popular to talk about this now. And I'm going to give you some quick thoughts about brain ageing. Actually, normal brain ageing is not my expert area, but I am part of this wonderful brain research in New Zealand, Centre of Research Excellence across the country, where loads of people are putting their brains together to try and come up with the solution for this. But as we age, we do know from our neuropsychology literature that our ability to acquire new information and apply learned information gets not so good as we get older. We all know that. We can tell that without me showing you a graph. You can see here a graph at speed of processing, working, and long-term memory and reasoning does deteriorate. But interestingly enough, people will say, my knowledge is not as good. It is. Actually, knowledge, in fact, if anything, gets better, doesn't it? Which is kind of interesting. So your idea about your intelligence and your idea about the world really does stay, in fact, still gets better with age. So it's obviously a real focus that we need to slow down this cognitive aging. And the Alzheimer's Society is sort of saying to us, if we can delay Alzheimer's disease onset by 5 years, that we will reduce the incidence in the world by 50%. That's a phenomenal aim. That's what lots of people are aiming to do. Now, really, in terms of normal cognitive aging, if you like, or aging that's called affecting our cognitive abilities, we need to build up a reserve as we age. This has become very popular thought, cognitive reserve, to provide a pool of resources that we can draw on. Now, it turns out that sort of things you might want to do if you've come along thinking I'll give you some information, really it's not hard to work it out, but the sort of thing that you're doing right now is the kind of thing you need to do. Stay engaged with people, stay engaged with education, literacy, come along and do things and get yourself engaged, and with people. There are programs like Senior Chef and Sago that are run by Age Concern that people can get involved in and know other people. And that's the kind of thing that even as you age will build up your cognitive reserve, so you've got more capacity there to fight this decline that goes on. But there really is evidence that the older brain has considerable plasticity. We say we can't learn so well, but there is real evidence that we've got considerable plasticity. For example, as you age, when you just put someone in a scanner and get them to do a cognitive task, you get activation across both sides of the brain. Now, what is that? Is that abnormal? Is that compensation? I don't know, but the fact is that areas of brain that weren't involved in the task before now are. So there must be plasticity capability in the brain, and the area we really find this is in stroke. If you know someone who's had a stroke, and most of us will, that you can recover incredible function. You can lose your speech with a stroke and have a almost normal speech 2 years later with really good therapy. It is very possible. Our brain is capable of doing it no matter how old we are. So you don't lose the ability to learn. It just takes more work, plus exercise, good diet, and sleep. I won't look at my wife because she'll, or my lab, because they'll all know that's not a thing I subscribe to very well. But anyway, we don't expect you to do things like this, but you do have the capabilities of doing it if you stay engaged. Now, how about enhancing plasticity in the brain? We've heard about, wonder drugs that you can take or pills that you can take that will enhance your cognitive abilities. Well, I think the upshot is, and I should really look at the neuropsychologists here, is that you've got to look at the studies very carefully. And if you hear about them and you see them in the popular press, take your study along to a neuropsychologist, they're the experts, and get them to evaluate it, because usually you'll find the science is not good, it's not got a good control group, the endpoints have not been appropriately decided, the time scale is not enough. There are very few of these I think are very convincing, but I think science is getting done better and better. So the sort of things that I want to talk about in terms very briefly at the end here about enhancing plasticity in the brain is neuromodulation. Now, the reason I bring this up is that there are things that you can get done as a normal person, if you like, such as transcranial magnetic stimulation. If you know a centre where they use these big coils they put out on the outside of your head and they blast them away, do these amazing things to your brain and then measure your function after. The other one that's becoming a little bit scary, actually, is transcranial direct stimulation. If you go along to direct current stimulation, you go into the chemist, you can buy one of these units for a couple of $100, sit it on the front and the back of your brain and turn on the 9-volt battery and run a current through your brain. You can do this if you wish. But can I just tell you as a cellular neuroscientist that we have no idea what it does? Sorry, cognitive neuroscientists, going to argue with this. And there are lots of studies that will give you really good promise that this is going to enhance your ability. One of my PhD student, Natalie, presented last year a wonderful paper, because Natalie loves mathematics. And she thought so what they'd done is they'd taken people who were not good at mathematics and those who were very good at mathematics, and they'd got them to do TDCS. And TDCS actually made the weak mathematicians better, but it made the good mathematicians worse. So I loved that study, it was brilliant. Okay. So just be a bit aware that we don't know what it does. It doesn't mean you shouldn't do a therapy you don't know what it does. A lot of clinicians will tell us here there are drugs that we use that we really don't know exactly the mechanism, but they seem to have worked, some of the discoveries that have been made. But if I'm going to blast my brain, I'd like to know what it does. And then, of course, there is this deep brain stimulation, which is used for Parkinson's disease. It's not really a plasticity enhancer, but it's designed to turn off areas of the brain. It works fantastically for certain people with Parkinson's. But the one I want to focus on is this extradural stimulation. You have an implanted stimulator that doesn't penetrate the dura. It's on the outside, but under the skull, and how that could be used to enhance function. Not necessarily in normal people. It's not the sort of thing that's... Somebody's encouraging me to dance. Okay, right. That was a nice little interlude. It's not the sort of thing you would do as a normal trying to enhance your cognitive function. But I want to show you how we've come to start using this, really. The first thing is that we've done quite a lot of work with transcranial magnetic stimulation. I don't know if John's in the audience, but John Schemmel, my colleague here, has got us into TMS here. Unfortunately, sadly, he's leaving us in the next few weeks, which is very sad. And here's some remainders of people in my lab and some collaborators where we've tried to work out what does this big magnetic field do inside the brain at the synapses. We're not there yet. It's very hard. But what people will tell you is that if you apply a certain kind of repetitive burst stimulation, an intermittent burst, so you burst and then you stop and then you burst, or a continuous where you blast it, that you can do opposite things. You can make brain excitability higher with ITBS or lower with CTBS. And there's a lot of literature come out saying how reliable and how good this is. But then you get the honest literature where they take a series of 50 people and they run them all through this and they give the same paradigm, which is supposed to make things good. If you look, here is the strength here up and down, here is the time, and here is what happens to different individual participants. And if you like the average there, it does absolutely zilcho nothing. Okay? Now, I think there is hope for this if we can understand it. There is hope for using this kind of thing, but we need to understand how, under what circumstances, to apply it. And there's some good work being done around the country looking at what factors might be predictors for relief of that. But at the moment, the jury's out. At work we did with John, actually, we could find that ITBS did increase things slightly, but we're talking about this line about here. It's not very much better than sham. And now Natalie in my lab here has been really trying to work what's happening at the synaptic level. And actually, if you look at her data, what it really shows, if anything, is that synapses get weaker, considerably weaker with that ITBS when we were always told that excitability would get better. Jury's out, we're still looking into it. But what about neuromodulation after stroke? And if you think about a brain here where somebody has a stroke, and what happens is that normally before we have a stroke in a normal brain, one side of the brain tends to counterbalance the excitation on the other side through inhibitory connections between the two of them. So we all know that this side of the brain controls that musculature predominantly. So you can see that here drawn by those crossed. But also one side of the brain tends to tonically inhibit the other. So things sit in a nice balance of mutual inhibition. So when you want to move, you have to relieve the inhibition to enable you to do it. Very simplified way of looking at it. But in a stroke, this does get a little bit vamped up in the wrong way, because you lose this ability to move your muscle, as you know, but you also lose this inhibition. And the inhibition means that the side on the other side becomes hyper-excitable because it's being less inhibited. When it becomes hyper-excitable, what it does is it tends to over-inhibit those areas around the brain that you really want to take over the loss function. Right? So rehabilitation works hard to do this very thing, to find areas of the brain that will take over loss function. But if it's being told to shut up all the time, it's making it much harder for it. So, increased inhibition hampers stroke recovery. So this has led on to some research that was done in my lab with these wonderful people here, particularly in Norwich, Melissa and Laura, who did their PhDs with me, and my colleague, rest of my colleagues, some of them are here, where we looked at using implanted electrical stimulation to improve stroke recovery. And we use implanted because we could use low intensity that we thought would be more focal. It wouldn't be a general activation of all of the cells. I think TMS doesn't work because it just activates all the excitatory, all inhibitory together, and basically the overall result is very little. So by putting an electrode actually on the surface there and using low intensity and using this burst stimulation, Melissa Barry in my lab actually absolutely accidentally found this finding one night and told me the next day that she could actually remove this inhibition. So I'll show you that again. She gave a burst stimulation and this inhibition went down for the period that she could record from the cells. And we thought, wow, that's really interesting. And I think it's what we've done is we've actually turned down the synapses, the inhibitory synapses from this side to that side, if you want to know the truth. It's very hard to know exactly the mechanism. Laura and Jason and others have taken this further on and actually looked at what happens to rats when we have these have this stimulation in, and we find that rats that have had a stroke, this is percentage recovery, this intermittent theta burst stimulation gives them great recovery. And what's very important for the next slide to know is that look at the variability here. It gets much less when you use this particular kind of stimulation, because the ones that were the worst to function got so much better. And that's really important to think of for the next thing, because there isn't a lot for people who are pretty severely affected with stroke. Notice my wonderful colleague up in the corner, my colleagues actually, Lee Hale and Professor Dirk de Ridder. So we wanted to apply this, we wanted to translate this. And it just so happened that I was very lucky to have a conversation with Professor Dirk de Ridder in Perth saying, wouldn't it be great to do burst stimulation? At that stage, he is the only one in the world that had the ability to get stimulation companies to do burst stimulation. The only one. And guess what? He came to Dunedin. So I'm sorry to revere you, but it's very important. So he's brought the ability to do burst stimulation with these IPGs as implantable pulse generators to Dunedin. We're the only ones in the world who can do it yet for this application. So we wanted to try this. We thought we'd give it a go, and we got some money from the National Science Challenge. Myself, John Schemmel, Lee Hale, Nick Cutfield here as well, and Dirk. And so what we've done, and we've run a feasibility and safety trial. We've only done 2 people so far. We've got results on 1. And what we're doing is actually putting an electrode on the top of the dura on the opposite side to a stroke with someone who's affected in their upper limb function. And the program that we do is that we assess them at baseline at 6 weeks, 12 and 24 for their upper limb function. Everyone who gets on the trial, so we've had controls as well, 3 controls, everyone gets rehabilitation, which is kind of cool, because some of these people have been 2-3 years out, they've had their rehab and they're kind of stuck with whatever level of function they have. So to have a chance of intensive rehab, it's not for the squeamish, because it's every day for 12 weeks, is welcomed by lots. So they do their rehabilitation, we assess them, and then we assess them again 12 weeks after that program's finished. The people who are implanted, we either give them immediate start, so they've got the stimulator in, we either start that off immediately and combined with rehab, or we wait for 6 weeks and start. They don't know which group they're in, and neither does the therapist assessing them. So the one participant we've had so far, we've got all the results for, was in the delayed start. This is a gentleman who was 58 years old, and he had a stroke here, which if you know anything about these MRIs, you can see these white areas. He had a stroke around his internal capsule basal ganglia, so he was impaired with his upper limb function. And in fact, he was much more impaired than the controls that we had. And what we did is assess him here and assess him here. He didn't know the stimulator wasn't on. In fact, he thought it was. But actually with him, rehab did nothing, which was really quite surprising to us because the controls did quite well. And we think it's because he was so impaired. Doesn't matter what these things are, the indices here of the ability to activate muscles and here really the functional capabilities. But the important thing is this is a scale up to 66 up here, and he had a number of 25. And after 6 weeks with rehab, he made no gains at all. But we turned the stimulator on, we carried on, every day he came, did the same old thing. What we would do is we'd pretend to turn the stimulator on for the first 6 weeks, and then he did it, and this is what he did. Now, I've shown this internationally, I've shown this to rehab specialists in AUT, and everybody gapes that knows about this stuff and says this can't be an accident. So something miraculous had happened to this gentleman. He's a very interesting guy because he quite often wouldn't say to you, I feel much better, but in fact you knew he was feeling better overall. And then we'd turn it off and we'd bring him back 12 weeks later. In fact, he'd lost function because he had no stimulator on. The fact is that it's sitting in there. It could be turned on if we had the approval to go ahead and do it. But it did still mean that he could actually had a grip strength. No grip strength at all. He had 10 kilograms after the start of it, and he could still grip 8 kilograms after. So we'd made a functional difference. If you can move your hand and pick up a glass when you couldn't before, it's a huge gain. So we're very pleased. We've got another person going through the therapy now. He's had his surgery last week, and things are looking good. To the future. What have we got to look forward to in this wonderful neuromodulation? Portable TMS. You don't need an operator that knows what they're doing. You can buy one of these, and you still can do this, actually. They actually started to do some clinical trials, and neurologists will know this, on migraine, and it does seem to be an effect, but you've got to carry this giant coil around and go, ah. But it does apparently, if you've got intractable migraines, people that you usually have, you'll know that it's worthwhile to do it, but very expensive. Ultrasound, I've talked about ultrasound, how we're going to put it non-invasively, that people are trying to actually activate, instead of our liposomal system, brain cells directly with ultrasound. I say we have to be careful about this and do very careful trials because you can fry your brain with it. This is an exciting area. Believe me, we will have some human advancement in this in the next 10 years, I believe, probably less. We can nowadays do this with experimental animals, that you put a virus in there which carries a construct that will go into specific types of brain cells, so one type of brain cell, and make them express light-sensitive proteins. And what you do is you put a fibre in there that drives light. Those cells will all activate with exactly whatever you tell those cells to do, just one cell type. So that can be done now, and I believe that the pathway is becoming open for it to be done in humans. And if it makes a difference with neuromodulation, the ability of someone to move, then we need to look at it carefully. Intelligent implanted stimulation, we can do this now with epilepsy, where you actually can record from a part of the brain with the same little stimulator that sits on the top there. And when it detects the seizures coming, it'll turn on the stimulator automatically and stop the person from having a seizure. That can be done now, actually, and I think it will become more prominent. And then there's all crazy things like Neurophotobiomodulation, which can be, people are thinking about it for cognitive function. That's kind of a fairly exaggerated picture, but we could be looking at scenes like this in the future. But I'm going to maintain that we need the cellular research to understand the effects of the full range of parameters of these, because otherwise we've got this parameter space that's so wide and impossible we don't know where to start. So we need to be able to break it down with some good research before we can really get predictable benefit. And I think you'll see that my journey really has been quite a happy marriage of electronics, neuroscience and medicine. It's all come together, even though it was a funny pathway to get there. So I'm just finishing with some thanks now. And I don't want to thank everybody. I can't thank everybody. I'd be thanking a whole lot of you here probably. But I just want to name some specific, or show some specific people. These are the engine room team. These are the PhD students. They're the people that get, I've got 12 there, 6 women and 6 men. So why haven't we got 50-50 representation in senior academic positions of women. Anyway, I'll stop there. But anyway, wonderful people that get you up in the morning. All of them have been fantastic, a great journey to work with. Some of them have will go to the lab and sit there for 15 hours trying to record from a cell, knowing they're only going to get one of these every 3 weeks. You know, so they're pretty incredible people. And this is my lab in general. You can see we have fun. I think all of you will spot yourself in there somewhere, if you can see. Some of you had to be photoshopped in, but they're there like over here. But quite good at Photoshop. But they're there. Thank you all so much. You've been fantastic. And I really want to acknowledge, and there are one or two I'm sure missing off here, but really particularly Otago collaborators, mentors, friends. Everyone in this photo gallery are at least 2 of those, and some of them along the way have become 3. So I thank you all very, very much. And finally, some really important people, the support staff of our departments, Department of Anatomy and Physiology. I started my life in the Physiology department, and I still see them all to say hi. Surgical Sciences have become friends. We've worked hard with the work we've done with Dirk. Health Sciences Divisional Officer, my new friends with my new job. That's another story for another day. Otago Medical School and the School of Biomedical Sciences for support. Funding agencies, lots of them along the way. Lots of grants written though, of course, that you don't get successful. Research centres, and last but not least, the students, because they're the people that we do all this for. So thank you.
Wow. Kia ora tātou. Kia ora, John. That was epically good. Epically good. And I think I could reflect on your scientific achievements and the research that you presented and the translational differences that you are making with your research. But and I also hope that your dopamine reward system is now kicking in to action in a very positive way. Yeah, I'm sure food's sort of sitting there too. But your reward-based centres should be kicking into overdrive, because that was fantastic. And I think you've got the acknowledgement from the crowd, which there's probably, you could come up and do it again now, couldn't you? But we won't form a habit of that. I did. I've reinforced it, and I've taken some notes. I mean, my job is to thank you, and I think the applause says much of what I wanted to say, which is that was wonderful. But I want to focus actually on something that's really important, because this is actually very special to me, because not only are you a member of our department, but you're also a very good friend and colleague, and so it's kind of nice to be able to acknowledge your achievement over a journey that we've shared for about 10 years now. And one of the things that distinguishes John from pretty much most academics that I know is not that he is a superb intellect, which he is, a great friend and a great colleague, but his passion. And John cares. Okay, he cares at every level. He cares about the service to the university. He cares about supporting the students in his research laboratory. He cares about delivering a great lecture to you and to me. He cares about giving that similar performance to every undergraduate class that he gives. And that, I think, is a mark of great distinction. And so your professorship is incredibly well deserved. I know the work that's gone into that, but I hypothesise to you that it's a byproduct of your caring, and that it would have happened anyway. And now the trick is, I think, to take the next step in your journey, because professorship is a fantastic achievement, but it's not what you set out to do. I would hazard a guess that what you've set out to do is to change people's lives by finding ways to remodel the brain after injury. And, you know, I encourage you to continue to find that dopamine reward-based habit of finding ways to take your research into a domain that will change people's lives. And I know that that is a journey that you will take, because you've shared with us how personal that is. And I acknowledge that. Anyway, I could go on and have a reputation for doing so, but I shall cut myself short and just ask you to join with me up here and accept this gift on behalf of the university. which will enable you to remember this momentous occasion, and also something which will enable you to increase your aging brain's potential to remodel.